Hey, how's everyone doing? Had the mic on mute right there. Can we do chapter 7, problems, standardized test scores? Oh, that's a good one. Covers a lot of topics, and we got Muhammad's question next. Let's just jump into it and start up some chapter 7. So we're going to get chapter 7 up and going right now. So let's go check it out. Chapter 7 for 201. The standardized test score one is a pretty tough problem. And I think, is it posted? Let me see if we have what we want posted right now. So we're going to get the standardized test score, and then we're going to do a little 474. But the standardized test score one, do we have posted my favorite thing? And you'll get to hear some tips right here. Let's go check it out. Modules. I don't think we have the solver posted, so I'm going to post my solver. We do. Yes. Oh my gosh. Did I put that in the blueprint? I hope I did. It's going to make life a little bit easier. I'll show this here in just a moment. Awesome. Okay, let's get the assignment up and going. And we're going to get the assignment up and going. Put a little chill music here in the background. But how is everyone doing? I see with Muhammad here and Tiffany here and Roger. Good to see you, Roger. I'm about to go to IMNT 342. How is IMNT 342? That's the database management one, right, Roderick? So that's a really, I've heard this is a tough class. I've heard that's one of those classes that you learn a lot in and pretty tough. My head tired today. Opening up the assignments for 201. It had shut down my Pearson on me. It logged me out. It said, no more. You've been gone for too long. It is Haslam Friday. Last week was the Pokemon Go weekend. Oh, did I find it? First click. Got it. Okay. Especially when you are the only one who makes the ERD and Visio. What is that? What is ERD? I don't even know what that is. Let's take a look here at the 201 question about standardized test scores. Pretty tough question. This one's tough. Let's do it. So what we have right here are standardized test scores for the SAT between 200 and 800. So 200 is the lowest verbal score, 800 is the highest verbal score, 200 is the lowest math score, 800 is the highest math score. The electron, oh, cool. I guess, yeah, I don't do a lot of that stuff. So I use different types of stuff. And so the verbals and math scores of a high school graduate class are displayed in the scatter plot with the regression line added. Describe the relationship. Well, is it positive or is it negative? Definitely positive. Is it moderately linear? Well, it has to be, because that's the only option. Students with higher math scores typically have higher verbal scores, vice versa. So pretty easy right there. Starting off nice and easy. What are our conditions for correlation? Everyone should know this. We were just covering this in 320. What are the conditions for correlation? What do we have right here? To do correlation, we must have this. Or regression, which is based on correlation. We were just talking about it in 320. What do we have right here? Mubot, is Mubot awake? Mubot, wake back up. Wake Mubot back up. Mubot is waking back up right there. The world is gone. Mubot's back. So what do we have right here is the conditions for correlation. Very important to know this. Hey, what's up, Cliff? Mubot's waking back up. He'll be here in a second. So what do we have as the conditions for correlation? Something, something. There's Mubot. Something, something. There goes. Something, something. Something, something. No outliers. What is the conditions for correlation? Then there's a fourth one, which we haven't covered yet. The fourth one is the plot doesn't thicken, which won't be a problem on this one. The same thing as the homework. So this should be the same as the homework. So this is the same one as the homework right here. So what do we have right here? So this is, what are the conditions for correlation? What are the 4 conditions for correlation? So remember, we just want to practice. We're going to be like, we have 4 conditions for correlation. The last one is plot, or we have 3 conditions for correlation, 4 conditions for regression. So the fourth one for regression is plot doesn't thicken, which we will be learning. And then what are the first 3 conditions, which are the same for correlation? The first one talks about the variables we must have. So we must have a certain sort of variables for this. So we must have a certain type of variables. And what type of variables must we have right here? To do regression, we need these types of variables. That's the first condition. The second condition deals with the line right here, saying it follows a what enough relationship. And then the third condition deals with this over here. So what do we have? Something, 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 none of these. So what is our conditions for regression? What are our conditions when we say we have must have this and this? To do a scatter plot, we must have those. And then right here, we must have a relationship that follows this well enough. It must follow this well enough right here. So what must that follow well enough right there? And then we must have none of these. So it's good to check to make sure you know the 3 conditions for correlation. What are our 3 conditions for correlation right here? The 3 conditions for correlation are the variable types that we need. So we need 2 of these variables. No outliers exactly. And then what are the types of variables we need? So we need what types of variables? To do a scatter plot, we need these 2 types of variables. So we need these 2 types of variables, this variable, and then we need a what enough relationship. And then we need no outliers. And then the last condition, which we'll be learning, is the plot does not thicken. We don't want the plot to thicken. So what do we want right here? We want 2 what variables, a blank enough relationship. And I saw right there, Tiffany, 100 points. Q, 2 quantitative variables, straight enough relationship, no outliers. And then the last condition is plot does not thicken. So we definitely have what appears to be a straight enough relationship. Well, we do have an outlier. And that outlier right here is at a verbal score of 200 or something and a mass score of 800. So we do see right there an outlier. So that's not too good. We have here the correlation for the data is 0.62. Now, what we can get from correlation is we can get R squared. And R squared is simply found by taking correlation and squaring it. And this will give us R squared right here. Great job, Tiffany. Excellent right there, following along. Great job. So this is going to be the R squared right here. And the R squared is going to be the percent of variation in Y explained by the variation in X. Very important that we have these notes over here. Where'd our notes go? Oh no, we lost the notes for today. So blank percent of the variation in Y is explained by the variation in X. Let's take a look. 38.4% of the variability in the math score is explained by the variability in the verbal score. Correct. So we want that the math, 38.4% of the variability in Y is explained by the variability in the verbal. So the math is being explained by the verbal right here. 38.4% of the variability in the math score is explained by the variability in the verbal score. Now, this is where this problem gets a little bit more difficult. And this is where you should go immediately to the regression solver. Do not solve this by hand. We will not have you solve this by hand on the test. We will not have you solve this by hand on the test. This is why I created the Regression Solver Pro right here, which you'll find and you can use in Microsoft Excel. So this program I created here, that's from review. So if you go right here and download the Regression Solver Pro and open it up, you will get to the Regression Solver Pro that I created right here, which will do the calculations for you depending on what kind of data you have. It is below or above. Oh, did I select the wrong one? Let me make sure I got the right one. Oh, let's see. Oh, it's above. Thank you, Tiffany, right there. Good catch. I didn't see that they're both the same. They differ on the end right here that we'd expect people to have higher scores. This is talking about the direction right here, Tiffany. So good catch. I said below, which would indicate a negative relationship. We want above. I was just focusing in on the R squared, but this right here indicates the direction of the relationship. This would indicate a negative relationship. That's where we make errors. Good catch. There's another 50 points right there. We would not say it has a negative relationship. We'd say it has a positive. And I did make an error right there. I didn't catch that little difference that this says below, which is negative relationship, and this says above, which is positive. This next one right here, once again, we need the regression solver on. And with the regression solver, we get the verbal scores had an average of this. Let's go ahead and bring up that regression solver. And it's basically going to do all the work for us because we would not do this on the test. This is just, I made this for this My Pearson problem because we're not going to do this work on the test. Let me zoom out here a little bit and make it so we can see it. Now be very careful. The right here, the Y variable's mean, we're looking for the mean of what? The Y variable is what variable here? This is how you have to be careful in using it. The Y variable is what, math or verbal? The Y variable is what? So the Y variable is what right here? Which variable is the Y variable? So we have to look at this and say, okay, we want the mean of Y. So we'd be looking at the mean of what variable? the mean of y is the mean of what variable? The mean of y is the mean of which variable? So look at the graph up there and be like, okay, the math, exactly. So when we go down here to the numbers it gives, we have to say the mean of math is this. So that's going to go right here. And then we want the mean of verbal, which is 510. Then we want the standard deviation of the y variable. That's the standard deviation of the y because that's math, and that's the y variable. Make sure math is the y. So that's the standard deviation. And then the standard deviation of the x is the other one because that's the verbal variable. And then we need the correlation, which is 0.62. They hide that. And now we get the equation. Here's the intercept, which is B0. You'll enter it in. You'll enter in your numbers. Make sure to look at your graphic. Math is the y. So if you were looking at the mean, this is the mean of math. And the standard deviation of the math. And then the verbal. But go. Where will you go? To get the Excel sheet, where will you go? Under the modules. So go to the modules. And under, you should see right here, where do we put it? Here it is under chapter 7. This is where to find it. So under the modules section, go here to chapter 7 and find the Regression Solver Pro. And then you can use it for these problems. I ask you to do these because we don't put these equations on the test. So rather than, if you make one little math error, everything goes wrong. So I made a solver for it because I was like, we don't do these equations on the test. Having this solver right here would be a big help. So I made this a few semesters ago, and it definitely has helped drastically with these problems. So make sure you know which things to enter in, though, because when we look at this, we need to make sure we know the math is the y. So this right here and this right here relates to the y variable. And then this right here and this right here is the x variable, which is going to be for verbal. And then when you go down here and look at the output, make sure to see that we have the verbal average. So that would be right here. The average for verbal is the x. Look at that's 510 right there. And then we have the standard deviation for verbal. So that's the x variable once again. The standard deviation of the x variable is verbal. And then we have here the standard deviation of the y, which is math. And then we have right here the mean of y, which is the mean of math. Does that make sense right there? So we have the different variables of interest. And then we have to enter in the correlation, which is given right here. There's the value of correlation. So that is the value of correlation. And we enter in all the values, and guess what we get? We get an intercept. Put the intercept right there. And then we get a slope. So when you're looking at these values right here, let's review again. You ready? So looking at these values right here on the screen, if you see verbal, verbal goes in the what spots. So verbal is the what's. If you see verbal, awesome. Great job right there, Colin. Thank you so much, Colin. If you see verbal, verbal goes in the what. Verbal will always be a what variable. Verbal will always be a what. If you see verbal, it'll always be a what. Verbal will always be the x. And when you see math, math will always be the y. So when you go down here and read the output, it says the mean of verbal. So remember, verbal's an x. So we have here the mean of verbal. So that goes in the mean of x because verbal's the x. And then it says the standard deviation of verbal because that's still the standard deviation. The mean is this and the standard deviation is this for verbal. So that's going to be the standard deviation of the x. That's why 172.4 is there. And then the mean of math, which is the y variable, is right here. And then the standard deviation is going to be right here. And then the correlation of the two variables is going to be right up here. I can't see it. There we go. There's the correlation right there. So just make sure when you're looking at this, you understand which is the y variable, which is the x variable, and knowing that we're talking about the mean for one variable, the standard deviation for one variable, the mean for another variable, the standard deviation for another one, and also the correlation. And then we get from that the intercept value, which is when x is equal to 0, and the slope. Now, a good check to do is to ask yourself, does this hit at about 189? It might look like it doesn't. Ooh, did we just click a new thing? We did. My Pearson, how dare you? Should be that. Let's say we got it wrong if we re-click it. This actually goes down below right here. Great job, Cliff, right there. Excellent work. This goes further down below because it doesn't actually show the y-intercept right here. So I hate that. That's a little bit deceptive. It actually goes further out because 0 is not down here. And then the slope does look to be about a few units. So I think we've done that properly right there. And there's a positive slope. So when we interpret the slope for this model, we would like to say for each 1 unit increase in somebody's verbal score, because that's the X, we would expect their math score to increase by B1 units. So for each 1 unit increase in their verbal score, the model increases an increase in their math score. So it's for each 1 unit increase in X, and the X right here is the verbal. So since verbal is the X, for each 1 unit increase in X, we expect Y to increase by B1 units. Now we get to the more difficult problems. Predict the math score of a student who has a verbal score of 733. Now, this is where you have to solve this equation, because what are we going to do right here if we're trying to predict the math score for someone who has a verbal score of 733? So how would we predict which Y hat is the predicted math score? How would we predict somebody's math score if they made a 733? So take a moment and think, you know that person made a 733. How would you then use this line up here to make a prediction? And what would you do on here mathematically? Exactly, Tiffany, right there, another 50 points. You got it. Just plug it into the equation. And we're going to take 733, times it by this right here. And then we're going to add it to this. We're just solving the equation. Make sure positive numbers are added, negative numbers are subtracted. And we get about 640 right here. And now the last one is the big tough one. Round to the nearest whole number. I feel like I'm going to make one error. Don't want to make one error. Yep. So make sure just to plug in your numbers right there. Plug in the decimals right here. We'll pause for a second. So this is the big equation. And make sure to get the regression solver. Just helps with solving this. You could solve it by hand. Not a lot of fun. I've got all the calculations going on right here. And go ahead, once you get the equation, which you want to use all the numbers it gives you, you'll need to enter into all of these fields right here, the numbers it gives you. And then you need to enter in the estimate of the intercept and the estimate of the slope. That stands for B0, the intercept, which goes right here. Really? The model predicts... for each additional point... Okay, good. It didn't change my answer. If I get something wrong, I'm going to review to see if it misclicked on me. So once you have this equation right here, you can do this. But also, I forgot, I added into the Regression Solver Pro. Check this out. If we go right here and take and use 733, it'll actually give you the prediction. And there is the prediction we get of 639. So you can actually use the solver to get the answer. And it's going to carry more decimals in the background than we're carrying. So it's going to give a little bit more exact of an answer. So that is the estimate for what someone would get for 733. So you can use this to make your estimate right here. It's just solving the equation, but it's probably pretty good to go and plug in X. Are you doing all right, Tiffany? Is it making sense? Might grab some water here in a moment. How is it looking? This is a tougher one. And it uses the ideas of regression to make the prediction line. And you can see that is the line of prediction. And then from this, we can make predictions by plugging in a value of X. And this is what the equation would solve to. This is Y hat. This is the predicted value from the equation. So that is our predicted. And once again, probably try to solve it by plugging in the value of X right here, and you should get a predicted value. So now, let's take a look. If I have to continue on. Here, wait, I might have to continue on, Tiffany. I might have to, because we'll have to do another problem here. We might swing back around here. I'll do the last little bit, and you can pause the video. So for the last one, with the last one right here, what are we doing? It says every year someone scores a perfect score, and this is the real tough one. So pause the video and watch how we do this. What it says is every year someone scores a perfect score, and let's see what we know. This is the one we need to focus on, and like, how in the world would we even solve this? This goes back to a lot of the concepts we were talking about earlier today, doing regression. Every year, someone makes a perfect score. So what we have right here, when we do regression, is we have a value of Y, and we have a value of X, and we get a prediction line, which are Y hats. From this, it wants to know what the residual of someone's score is. So if we have values of Y right here, like if someone made a perfect score, then we could find the value of the residual. The residual is just this difference from what the person actually scored to what they were predicted to score. And so we can mathematically find this distance right here. So the equation would be what did they actually score minus what they were predicted to score. And that is going to equal to their residual. So we need to find this information right here to find the person's residual. The residual is going to equal their actual minus their predicted. So the thing you have to know about the SAT is if someone scores a perfect 1600, then that person's math and verbal score, we know that, remember, we have right here, verbal is the X. So verbal is down here. And math is over here. So math would be the Y variable of interest. And verbal would be the X variable of interest. So we have right here that that person's math score is equal to 800. And that person's verbal score is equal to 800. So that is their actual math and their actual verbal score. And from this, let's go right here. Let's take our equation. We're going to take this equation we have right here. And what will this equation now solve for? What is this equation going to solve for if we plug things into this equation? Plugging into this equation right here will obtain for us their what score. And what does that little hat mean on it? So remember, math is the Y. So if we were to take that X right here, which is their verbal score, what are we going to get? Who knows who's watching? If we were to take and plug in this value of X into here, so we take this X and plug it in, what do we get? Like, what is this over here going to be? So what will that get us? If we take and plug in what the person made on their verbal and solve that into the equation, that will get their what score? I'll give it like 1 minute right here, see what people think. So what is this going to give us? What will this give us? If we take and we plug in somebody's X value right here, and then we solve for that, what is that value right there? What happens when you plug in a value of X and you solve out? What will you get? Well, you might get that. You might get that mathematically. So what is that? Great job right there, Tiffany, 50 points. What is that? Like, what is that? That value we obtain right there is the what? So you are correct, I think. Let's check it mathematically. It might be. And so we get that. And what is that value? That is the value. So what is that? That's a good question. What is that? What are we seeing? The predicted value. Great job, Tiffany. Excellent work. 100 points. You're getting it. So that's the predicted value. So do you know what this person actually made on their math? The person actually made an 800. But they were predicted to make a 680.368. And that means their residual, actual minus predicted right there, actual minus predicted is 119,632. And so that is the person's residual, how much the model misses them by. And that's because this person, if we've drawn it accurately right here, is 119.632 units or points above what we thought they would get. They were higher than what the line predicted them to be. The line predicted them at about 680. They scored about 800, and the residual means of 120, which I'm just rounding it. The residual of 120. So how did I get their Y value? So this is their actual. That's their actual value, because residual equals actual minus predicted. So how did I get the actual value? Because what does the question state? It states every year someone makes a 1600, and the only way to make a 1600 is to make a 800 on the math and an 800 on the verbal. So by saying a person made a 1600, what they actually made, like this person actually made an 800, so their actual score was an 800, but they were only predicted to make a 680. So they made an 800, and with that, they would be predicted to make a 680, which is a residual of 120, which is just the difference in these. So is that, yes, Tiffany, excellent work. Yep. This is a lot of theory. You're covering a lot of class right now by learning this and understanding how we get the residual right here. These are some of the toughest problems on the test. Like this, if you understand this problem and can do it well, you understand multiple things. Let's take a look. 3 decimal. I think we have everything. What did I do? What did I do? I bet I misclicked something. Sorry, my head is a little hurting today. What did I do? That's right. Did I misround something? We are manually checking all the answers. Round to the nearest whole number, round to 3 digits. Oh my gosh. Yeah, I know, right, Tiffany? I don't know why I put that in. Oh my gosh. There we go. There we go. It's so easy. It's asking for what the residual is. And for those watching, don't worry. We know how to do it. We multiple times solved the residual for it. That was the whole point of the question, was to solve for the residual. I was like, what did we do wrong? Everything sounded right theoretically. So the residual right there is 119.632. Very easy to make a mistake, but follow through your mathematics, solving for the different values. The more you understand the notation here, that the verbal is the x value, the y is the math value. We know what the actual value is right here. You know what your residuals are, the actual minus the predicted. So the hardest part for people usually to do is you have to take and plug in your value of x right here and plug in 800. Because from this, you will get the predicted y, which you need up here. Does that make sense? It's a little bit tricky because you have to go and find the predicted value, and then you have to deduce the actual value. You have to say, well, they actually made an 800 because they made a 1600. And then from the line of prediction, you have to get their predicted value, and you would get this right here. So this is a tricky one. It requires multiple steps, but we got all the steps on the screen. It's always that they made an 800. So you would plug into the equation to get a prediction for somebody. So this is the prediction for someone who made an 800 on the verbal. And then we can get from the actual minus the predicted, the residual. And we've got notation up there explaining what it all means. Whoo, right there. Oh my gosh. Let's go check it out. Next question. Woo, big one right there. I can't believe I made an error on the end. Let's go check it out. Okay, I think Mohammed had a question on... Can we do question 4 on clustering homework 474? Let's go check it out. Question 4. Oh no, like my head started hurting back here today. No! Headache bad. Maybe it's too much looking at a computer screen. Can't have that. Let's go right here. I should get some of those blue light glasses. Probably good for me. Let's go grab that homework. Clustering, question 4. Homework for clustering. Download the RMD and the Kroger data. Let's go check it out. And here we go. Mubot talking away in the chat. Thank you, Mubot. Chilling out with us. Question number 4, getting ready for 474 clustering homework. Here we go. Let's go check it out. So there is no natural choice for number of clusters because there are no right answers. Let's make the choice k equals 3 on the Kroger scaled data. So we're going to have to go and scale the data. With 3 centers, we need to run a max iteration of 30. That's the maximum amount of times it'll try to assign the cluster IDs. And end start is the amount of times it starts over as it finds the cluster centers. So those arguments right there, itermax is the maximum iterations it goes through as it tries to find the centroid centers to the clusters. It'll either reach convergence or hit max iter. And the end start is the number of times the algorithm restarts to see if it finds a better one. You might say, why does it need to restart? The way it does cluster centers, like if these are cluster centers, it would randomly pick a point here because it's trying to reduce the within cluster sums of squares. So it's going to go here and say, here's a cluster center, and here's a cluster center, and then it's going to assign the points. It wouldn't have the colors yet on these, but it's going to assign which ones are closest, and this is not quite the same algorithm, but kind of a quick visualization of what it's kind of doing. Nice work, Tiffany, right there. That's worth 100 points. Congratulations. Great job. So there is no true choice to how many clusters we should use. This would be like a k-means 2. This is not a clustering scheme, but if we had used 2 clusters right here, that'd be k-means 2. We're going to use k-means 3. So print to the screen the contents of the rounded clusters with centers equals 2 to see the locations of the cluster centers, all that good stuff right here. And we need to first make our data. So we're going to do a little work right here on making the data. And let's go to where we clean the data. Here's where we're loading in the Kroger data. Load in the Kroger data. Make sure it's in your working directory. Very important right there. So the Kroger data has been loaded in. I'm going to delete off everything here. And let's load in the Kroger data. Kroger data loaded in. And histogram's looking at scaled data. We got a little bit of work here to do. Okay, in the global environment, you'll find a function called scale data frame. There it is right there, which takes the data frame as an argument and inputs the data frame for each numeric quantity to have a mean of 0 and a standard deviation of 1. Scale data, and scale data. So there we go. We're doing, and I'll explain why we're doing plus 01. The reason we're doing it, I think it says, because we can't take the log of 0. We could probably look at some viz. We might have time. We might. I think we might have time. That's a good question. And so let's go here. I think it's actually regression, which is one of the themes today. So we run this code right here. Left arrow, the result of running scale data frame into Kroger scaled. There we go. Run it. Good. And there's that. Then take the log 10 of each value. Then scale each column to have a mean of 0. And wait. This will take a penny. Yeah. We do that already. Run apply mean and see that it is all this right here. It has a mean of 0 and a standard deviation of 1. So let's run this. And these means are basically 0. These are scientific notation for tiny, tiny numbers. And then we go here and do the standard deviation. I did DF. What am I doing? That was right next to standard deviation. And the standard deviation is 1. This confirms, Tiffany, I'll throw a 300 point out here if you know. Since these have a mean of 0 and a standard deviation of 1, what did we turn all this data into? 474, you can also answer, all of this data here has been turned into what? I'll leave that question hanging. But now these have a mean of 0. You might say that doesn't look like a mean of 0. If I round it to like 8 decimal places, you can see those are all 0 and the standard deviations are 1. All of these variables right here have been turned into what? So they all have a mean of 0 now and a standard deviation of 1. And if you were to look at one of these in a histogram, it's going to look like, we'll go to the Kroger scale data. Let's go to drinks. And it looks something like this. Now, it's got an outlier there. That's not the best. Let's go here to another one, baby. And, oh, wow, look at all those outliers there. People probably not spending money on babies. Fruit and veg. So all of these have been turned into z-scores because they have a mean of 0 and a standard deviation of 1. Now, z-scores will not change the shape of a distribution. So we were able to achieve somewhat more normal of a shape right here. If you look at the original Kroger data for this, it's going to be... good guess right there. We turned it into z-scores, 100 points right there. This is the original data. This is the transform data into z-scores because instead of having these crazy units on the bottom, when we do clustering algorithms, we want things to have an equal say. So we don't want things to be too far away from each other. Tiffany, you're almost there to the top. First person to get there, Tiffany. You'll be at the 1.2, the total top tier. Great work. So all this great stuff, that's more of that question. We're down here on question 4. We now have our Kroger scale data frame. Question 4. Since there's no natural choice for the number of clusters, let's choose k equals 3. Run the k-means on the Kroger scaled with the centers, print to the screen the contents to see the locations, to get a frequency table of how many individuals are in each cluster, the labels, blah, 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 may identify, but you should always end up with the same values for cluster centers. So not quite. I want you to check your work. Not quite going to do the k equals 3. I'm going to go k-means. And we want to run k-means on the Kroger scaled. Make sure you use your Kroger scaled. See, it's telling you what to do right here. The centers is k equals, and I'm going to go k equals 5 because I want to. And iter max is how many times it'll go through iterations of assigning cluster centers. Did we say 25? I'll let you guys pick yours. I'm going to go iter max. I'm going iter max 100 because I like to. And n start is the number of times the algorithm will restart. I'm going to restart the algorithm 50 times. Cool. Oh, it's mad. It's mad. Unused argument, k equals 5. There. Now it works. It doesn't like the k for cluster centers. Is it centers? It is centers, isn't it? We were doing k earlier. Yep. So when you do this right here, it's probably good to set a seed. I'd probably set a seed before this. And we should have enough that we reach good convergence. And now we want to go here and go to k-means and store into it. A little bit iffy on calling it k-means since the algorithm itself is called k-means. So you won't quite get the same thing. You have the object k-means or a list right here. Good to see you here, Trevor. We have the list k-means, and then we have the function k-means. So this is my list right here, which we could open up and look at what's inside the list. And we could also look at the k-means algorithm. So when you run this right here, an important thing to know, and let's take a look at this. We're going to do this as a for loop for a second, because we could run and do this for multiple things. This kind of goes to other portions of your questions. If you were to run the k-means algorithm right here with different amounts of clusters, and so let's write a real quick code right here, and within cluster sums of squares, and the k-means algorithm can let us see what the within cluster sums of squares are. So this is the total error we have, which is like regression with residuals. So if you were hearing about residuals in regression a moment ago, we're going to look at the total error right here, and we're going to take from this k-means and store into the within cluster sums of squares from the k-means the total within sums of squares. And let's go ahead and take a look. Here we go. Now, oops, I didn't do it right. I stored into it every time. Always look at what you make. So what are we getting right here when we run this? We are getting the within cluster sums of squares as we increase the number of whats. We have increased the number of whats we are using, and then we're looking at the decrease to the within cluster sums of squares because we're increasing the whats. Every time I'm running this algorithm right here, I'm increasing the whats. And the way this works with what I'm increasing right there is if we had, let's take a look. So if we had data that looked like this data would probably have 3 natural clusters to it. But data is very hard to visualize, especially with a high dimensional data set. If you have like 20 variables, it's hard to tell, like you're collecting data on how much alcohol do people buy, how much baby supplies do people buy, all these different things right here. It's very hard to visualize a high dimension data set because our data set alone has in it dimensionality of 13 dimensions. So if you're trying to visualize this right here to see where people are located, it's a little hard to tell which customers are similar, and that's the point of clustering. So it's much easier to talk about like a 2-dimension visualization right here, where we might try a 3 clustering scheme, but in truth, we could try actually a 2 clustering scheme. So you get a cluster center here and a cluster center here maybe. But why try a 2 cluster scheme when we could try like a 4 cluster scheme? Probably not how it would turn out. Why try a 4 cluster scheme when we could try a 5 cluster scheme? So you could cluster these things and the algorithm's going to do this for you. But what do you notice about the error as you go to higher and higher amounts of clusters? If you go to a lot of clusters, then the error within the clusters is going to get water. So here's with a lot of clusters and how far things would be from the cluster center. The error within the clusters are going to get water as you go to more and more clusters. Oh, good. That you were not happy. Oh no, I'm sorry. Let me know. I'll put out a thing that you can ask questions about. One of the true falses said like yes, no, and we'll be changing that because it's like, is this an outlier? True, false. So true, it is an outlier. False, it's not an outlier. I think one of the Tom Brady ones. So yeah, let me know. Email me. We'll take a look. There you go. Yeah, no worries. No worries. Some of them are tough. Some of them are tough. What would happen to the within cluster sums of squares right here? Oh, no. No, that's not our goal. There's tricky ones. They're tricky. They're tricky. We try to do the tricky ones in class too. The within cluster sums of squares is going to get water. The within cluster sums of squares is going to get Oh no. Yeah, I think it shouldn't have been true false. And Terry, we'll talk to Terry about it and I'll mention all these things. But I think that was a new one this semester and I saw it too and I was like, oh, that should really be like yes, no. Like, would this be considered an outlier? It's not really true false. It's like yes, no, but yes, it's considered an outlier true, or false, it's not considered an outlier. This would be considered an outlier. Shouldn't have had a question mark on it. Like this would be considered an outlier, true statement. But little confusing, and definitely we're gonna talk to Terry, and Terry makes all the decisions. He's got the high pay grade. So with this right here, what would happen to the within cluster sums of squares? It's going to get smaller and smaller and smaller. So the within cluster sums of squares is going to get smaller and smaller and smaller. And take a look at this. This is what we're seeing with these numbers, but we can also see it very clearly. And who knows, for 100 points in the chat, what do we call this right here? What is this thing right here that I've created called? Which actually would indicate to me we should probably use about 4 or 5 clusters. What is this graphic right here called? This is letting us analyze the within cluster sums of squares as we increase the cluster centers. As we increase the cluster centers, what do we notice to the within cluster sums of squares? As we increase the cluster centers, the within cluster sums of squares is doing what? And what do we call this? This is going to be called an elbow plot right here. So when we look at this right here, we need to think about what an elbow plot is, and it's helping us look at the decrease to the within cluster sums of squares as we add more clusters. Now, what you don't want to do, well, one, you don't want to run the algorithm this way, but also if you were to run it with something ridiculous here, like 300 clusters, which might take a moment, what you'll see when you do this is you're going to get a very small within cluster sums of squares, but that's because as you increase the cluster, the amount of clusters, you will decrease the within cluster sums of squares. This is a ridiculous way of doing this. I don't know of anyone who would do 300 clusters, and probably because we didn't do enough iterations, we're not seeing it converge. But really, this is not a good way. Really, in here, we're getting that really good return, and I would do that right there. Getting messages from it. It's from CVS. So with this right here, we are seeing the decrease to the within cluster sums of squares, which will approach 0 as we increase the cluster centers. Thanks, Scott, for this. Carter's interested in using cluster NAs to help aid. Just found algorithm at the end of the algorithm. Determine how each of the clusters differ from each other. Then explain why would Kroger not find this cluster scheme useful. So if we're looking at our cluster centers right here, let's go back to a real one right here. So to go back to a real one, we're going to take our code and let's do a real clustering scheme with, let's say, 5 clusters again. And sure, 50 and 200, why not? Make sure to use the numbers in your problem. And let's go here to the k-means. And in the k-means algorithm, let's go here to the centers. There's the centers, awesome. And these are standardized metrics. And would Kroger find this useful or not? Actually, they might find this useful. Wow. Well, these are the customers right here who are really not buying anything. So you need to look at yours and be like, what's going on with your cluster centers? Let me change this to rounded and put in 2 decimals. Better. Make it wider. And we can see right here, and let's make it only this output. We can see right here, these are the customers we are losing. These customers right here are way below average. These Z-scores are very, very below average. These are the average customers, and maybe this isn't so useful because we're just saying, like, here's your customers who don't buy stuff. Here's your customers who spend on average what you would expect. Here's your slightly above average customers. Really, at least with my clustering scheme right now, there's nothing that stands out about these customers. There's no real unique thing except like below average customers, above average customers. So I would say I don't see any real standouts here. Like we've got very below average, average, average. It's not really, I'm not really liking this as a good marketing scheme because if they're looking to market individual products, like people who cook, this person right here for cooking, it's just they don't cook because they don't go to Kroger. This person for cooking probably cooks because they go to Kroger more than most people. But they cook more than most people because they go to Kroger more than most people. They're not like, I love to cook. They're just like, I go to Kroger more. This person doesn't hate cooking. Well, they might be our person who hates cooking. No, but they've got other values of that. They're similar in all interests. So we don't really see any standouts where this person's dislike for cooking is a standout. Would we ever get a standout? Let's try 8. Do we have any standout characteristics with 8? Trying to see if I see something really big. That's big, but this person just hates everything. Oh, this is our people right here. I like it. These are my Kroger customers. We might have found something. We got one group of customers. These are the Kroger customers who don't go to Kroger much, but they really don't like health stuff. So these Kroger customers don't go to Kroger much, and they really don't like health stuff. That's the biggest one I see that breaks the trend. They're below average and everything, but they really stand out in this. Let's try one last thing right here. What do we get right here? That's a big standout, but they really are below. So we're not getting any really distinct characteristics. A lot of z-scores close to 0. And we made a lot of z-scores here. So nothing really distinct, nothing really jumping out right there. Let's take a quick look at the next visualization. So let's hop back here. Let's check it out. So the next visualization for 201 is over regression. Let's show how to do it. We might not explain fully, but I've got a great video on this. If you didn't know about the visualization playlist, check out the visualization playlist. Let's kind of mention that here at the start too. So we're going to show how to do this a little bit here, but I would highly suggest the visualization playlist. Visualization assignments. So let's go show that here, and let's talk about the next visualization. Here we go. 201, visualization number 5. So I would highly suggest the regression and the interpretation. Oh, we get to see some Smash Bros. I'll let you click on it to see the Smash Bros. And we talk through what's going on. People probably do that. I do that too. Make sure to do your visualization, but we'll go through how to do this and make sure to follow your questions with your answers with Long Hair Brian from the past. So let's go ahead and take a look at this visualization here. We just have a moment. And let's jump into 201, grabbing the information. Visualization number 5, I think, due next Wednesday. So when we do this regression visualization, here's what ours looks like this semester. We will need to make sure we outline these very important 4 things right here. Name the 4 conditions for regression. Yes, of course, Tiffany. Thank you, Tiffany, for asking. So if you're looking at the chat right now, let's drop that link in the chat. Here is the link right here. I'm just going to spam it a few times. 1, 2, 3. So there's the link right there. Make sure we have the link. And that is the link for the regression video. Tiffany, I bet, do you know the first 3 conditions for regression? So let's see if we know the first 3 conditions for regression. Think about your correlation conditions. Q, straight enough, no outliers. And I was mentioning earlier on the 4th condition from earlier in this video. The 4th condition is going to be plot does not thicken. So we'll talk more about what that means in a second right here. We have to get the residual by predicted. Oh, wait. Your screenshot of the output must include the screenshot with the regression line, all the regression output, titled linear fit, and only the first residual plot titled residual plot by predicted. You can take multiple screenshots if necessary to display the output. So this is a big thing. I think this was added on this semester right here. Make sure to have your residual plot. The residual plot will be included in the output, and we'll take a look at that here in a second. Report the value of the y-intercept and its interpretation. Report the value of the slope and its interpretation. Report if the linear relationship predicted between the two is statistically significant. Define and include the value from the output you use to support your conclusion. So let's take a look at this right here. Make sure you follow all of these steps and understand what we're doing with regression. To do regression, we must have what? So to do regression, we must have what? Which is the first condition for regression. To do regression, we must have what? Like, you're not doing regression or correlation if you have this. The very first condition of regression, which will ensure that we are doing regression, is that we must have what? And I'll help you out by doing this right here. I want to make sure I don't do our example. You'll take a random sample. So make sure to take your random sample. And then you must have 2 quantitative variables. Tiffany, great job right there. 2 quantitative variables. And then let's see right here, use caret and price. So I'm not even using the same data set. Good. So we have 2 quantitative variables. Let's take a look at which would be a good variable. how many Facebook friends people have, and does that explain if they've defriended people on Facebook? So we're looking at how many Facebook friends people have as the X, and blue means quantitative. Blue means quantitative here, and how many people they've defriended. Ugh. Don't like it. Don't like it. Let's see. That is not a great regression. It's got outliers, not really straight enough. Let's go to age. Does that explain someone's GPA? Yeah, it's maybe. All right, let's take a look. To do regression after you do the analyze fit y by x, we will go here, and we will go to the red arrow, and we'll go to fit line. So the fit line, how do I take a sample? To take your random sample before doing your regression, which is very important, go to tables subset, and on tables subset, make sure to put in your student ID number plus a 4 before it, I think it says. Let's double check so people don't do it wrong. 4 plus the last 2 of your UTID. So make sure to go to tables and then subset, and then go here to random sample and enter 4 plus the last 2 of your UTID. If that's your UTID, enter that in. But if it's not, make sure to do 4 plus the last 2 of your UTID. Now that we have our random sample, we can go over here to analyze fit y by x, which does a bivariate display of data. So when we do this bivariate display of data right here, we can analyze something like age, which is just how old somebody is, to see if that explains their high school GPA. So this is the x variable of interest, and this is the y variable we're interested in. Think of this. Does age explain why someone has a GPA of a certain amount? And so when we look at this, we need to then ask ourselves, well, is this possible to do a regression on? Is it a quantitative variable? And quantitative, it's a scatter plot, so yes. Is it straight enough? Kind of. It's mostly straight, maybe a little bend at the end. Are there outliers, which we don't want there to be? There might be outliers. So we're going to fit the line. This one is a maybe on regression. It's got problems-ish in some areas. It's definitely 2 quantitative variables. Kind of straight enough, kind of, and maybe an outlier. And then it doesn't look to have the plot thickening. Which variables to choose? I think you're choosing cut and price. So make sure to go through with your instructions right here. You'll be doing, I think, caret and price. There it is right here. So caret and price right here. Use caret as the predictor and price as the response. That makes caret the x variable and price the y variable because you're interested in. Activity 4 video, I think we'll be doing that. Awesome, Adam. Good to see you here. I think as long as I'm feeling all right tonight, I started to feel a little bit of a headache right here. So remember, x is the explanatory variable, and then y is the response. So we are trying to understand price right here. Does caret predict or explain the price, which is what we're interested in, is the response variable right here. So when we look at this output, here's the important stuff. 1, we need to get a residual plot. That is correct. Yep, great job, Tiffany. This is something I don't know that was in the last one, so I might need to make an addendum to it, like how to get residual plots. Might need to make that this weekend. So I don't know. I'm like so anti-drugs, even just regular old drugs, right? Hey, Kiana, good to see you here. Love seeing everyone here. Adam and Kiana, some points right there. We're going to add into here the residual plots, which I don't know if I have in the last video. Plot residuals right here. And we're only getting this one right here. Now, when you look at residuals, and this is the one we want, the first one it said, when you look at the residual, a residual is how far something is away from the line. So if you look at this output right here, we'll decrease it. Really? We will decrease it so we can see it. Eventually. There we go. If you look at this point right here, you can see how far it is below the line, and take a look, it's right there. At the very end of the plot, we should see 3 points. Oh, because it's reversing it. I hate that it does that. No. You can see where they're at in the other plots. I actually prefer this one right here. Let me make sure we're getting the right plot. Residual by predicted plot. Residual by predicted. Mine did not give the linear fit. How do we get the linear fit? Where are the options at in jump? How do we get the linear fit? Great question, Tiffany, right there. How do we get the linear fit? Where are the options at in jump? If you don't see something in your output, where should you click to get the additional options? If you don't see something in your output, where should you click to get the additional options? If you don't see something, where would you click? Always click the what's. To get additional options in jump, always click the wheres. Those red arrows right there. So the red arrows are where we go to get the linear fit. And then to get the residual plot right here, you'll also click the red arrow under the linear fit once you get the linear fit. So once you click the red arrow, there's the option to fit the line, which fits a regression line to it. We don't need the summary stats. Good question right there. We're just going to fit a line to it. So that's going to create a linear fit. It's going to fit a regression line to this model. If you do have highlighted points, I want to point out, click somewhere inside the graphic. It'll de-highlight them. That means you've selected rows if you see something like that. Hey, Zaid, good to see you here. We're finishing up some visualization number 5. Whoops. And so when it comes down to this, we're actually to the end of this right now. And I want to point something out because I'm going to take a quick break right here and get something to drink, get some food before I start teaching next class. The end of this right here, make sure to get these plots. Make sure to get these screenshots. This right here is new this semester, I believe. But I want to point something out. One of the most important things to know, is old Brian right there, is when you are interpreting these things right here, is to do the interpretations properly. And I go through here and explain, I'm zoomed in, or I'm not zoomed in. I'm explaining the topic by zooming in really far. That's too far, really? Something seems weird. Oh, that's weird. So slope interpretation right there. I guess I zoomed in really far. And intercept interpretation right there. When x is equal to 0, we expect y to equal b0. Over here, we can see, I think, did I write the conditions or did we not have the conditions last time? Oh, that's a pretty one. Do we use the same? Nope, different stuff. Does this look like 2 quantitative variables? Yes, it does. Drop and speed are both quantitative. But what might be the issue right here? If you take a look at this, and let's check our conditions, good checks for these, yours might be different. When we do regression, if you're doing the one from here, we have right here that we have 2 quantitative variables. So it is quantitative. Next, we need to check that it's straight enough. To do regression, we need to fit a straight line that looks straight enough. But now we start to see issues. I would say the issues is maybe that there's outliers, or the fourth condition dimension, the plot looks to maybe thicken in some spots. It looks like it's maybe thicker or thinner, so I would say this violates the conditions right here. So make sure you're checking your conditions in full by writing them down. 2 quantitative variables is met because drop and speed are both quantitative variables. The straight enough condition looks to be met because a straight line goes through the relationship of drop and speed. I would say we violate the no outliers condition maybe because there's some points that are far away from the straight line. Finally, the does the plot thicken, which tells us if this has a constant thickness, so constant thickness would look like this, where they follow a constant thickness, or we don't see a constant thickness, which is kind of exhibited right here a little bit, where it's got that like little bump in it spreading out. That looks like a violation of the fourth condition, the plot does not thicken. To get all the graphs and info, make sure I'll show it again real quick right here. To get all the graphs and info, once again, we'll make a regression right here. We'll go to Analyze Fit Y by X, and we'll go here to a variable like age to try to explain someone's high school GPA. Once we go here to Analyze Fit Y by X, we'll click OK, and then we'll click the red arrow right here, and we'll go to Fit Line. This will fit the regression line so that we can see the equation for the regression line and also the summary statistics for the regression line. This right here is the intercept of the regression line, which we can see. It actually goes further back, way back. Don't do this to your graphic. But the intercept is up there at about 6.1. And the slope of the regression line is the rise over the run, but it is negative here. And so to get the diagnostic plots, go to the fit line to get the residual plot. Oops, wrong button. Go to the fit line right here. And last but not least, go to the plot the residuals. So once you plot the residuals, it will plot the residuals, and we want to take a picture of this one right here. So I would say the residuals, does it look like this plot gets thicker in some areas? So this might violate, at least the one I've done right here, and you can make it a little bigger if you want. This one might violate the condition of does the plot thicken? You don't want to see it get thicker or thinner. You want to see a constant thickness throughout, and that looks to get a little thicker towards the middle, and there might be an outlier. So it looks to me like we do have 2 quantitative variables. And we'll make this look a little bit better by zooming back in on it. Oh, you can do this if you want to zoom in. Go wee. So it looks like, really? Oh, that's not the zoom in. We have 2 quantitative variables. I've used too much Plotly. We have 2 quantitative variables, which means we meet 2 quantitative variable condition. We have a straight enough-ish relationship. Good enough, straight enough. It's on the edge of it for me. Got a little bend at the end. And we have an outlier, it looks like. And then we might have some plot thickening. It might actually get thinner. And that's exhibited in the residual plot, especially where you can see like it's thin here and thicker. It could analyze yours. So look at how yours looks and then ask yourself, is it two quantitative variables? And then explain in a sentence. Does it follow a straight enough relationship? Explain in a sentence. Does it have outliers? Outliers are bad. We don't want them. And then is there plot thickening? And this is a good way to look at plot thickening. And then when it comes to the interpretation, here's the last thing. When it comes to the interpretation of the slope and the intercept, make sure to go through here and interpret your slope and intercept using these in slope and intercept interpretations. Make sure to interpret your slope and interpret your intercept, and then know how to talk about the statistical significance. So I'm going to put this in the chat again. I'm going to head off real quick, just take a quick break. But once again, in the chat right here, we have the link for the visualization video. It's a really great help, but make sure whatever you do, and I might send an announcement, to make sure to take this plot right here, because I don't think we had that last year, and include the conditions. I'll be back. We'll be teaching here in a little bit, and I'll see everybody then. Bye for now, everyone. Bye.